Okay, so here we have our matrices. Now I'm writing down a set of simultaneous equations. 2x minus 3y equals 4, 4x plus 2y equals 7. These coefficients, you can see, are completely mimicked by the numbers in the rows. The numbers in the first equation are in the first row. The numbers in the second equation are in the second row. The numbers in front of x are all in the first column. The numbers in front of y are in the second column. And the number to the right of the 0 is in the third column. Right of the equal sign, not the 0. Okay, so I'm going to reduce these using the same procedures you just saw. But I'm going to cover this up so that you don't see it in advance. I'm going to take half of the first row because I want this 2x to become an x. Okay, so I do that. Well, clearly half of this, that's that first row, half of multiplying through both sides of this equation by 1/2, this is what we get. You can verify that. I don't have to read it to you. Second equation is still as it was. Then I take -4 times the first equation and add it to the second. I'm going to get a -4x here, and when I add the equations, I'm going to add the -4x to 4x to get 0. So that's what I do. -4 times x is -4x, added to 4x gives me 0. -4 times -3/2 y gives me positive 6y, added to 2y gives me 8y. And -4 times 2 is -8. When added to 7, it gives me -1. Now this is a lot like what we did with just the numbers in the row, except now we have a meaning with x's and y's. Okay, so I denote that as I take the second row and add -4 times the first row, second equation, add -4 times the first equation, and I get this equation. Now I multiply the second equation by 1/8. And when I do, it's very clear, I get y equals -1/8. If I multiply this equation, both sides, by 1/8, this is what I get. And of course I've got 0 here, so you don't even have to write that down. We just discovered that y equals -1/8 is part of the solution of this equation. That's why we're doing this. There are other ways to solve simultaneous equations, but in linear algebra, the equations are always linear, meaning you always just have first powers of x and y, and equations will always have a form much like this one. So we can always do what I'm doing here. Okay, so anyhow, we get y equals -1/8, so that's handy. And at this stage, we could substitute that here and then solve for x. But we're going to do it by multiples of rows and so forth. So I want to get rid of the y here, and I'll just be left with whatever x equals. If I can make this 0, I'll have my solution for x. Well, if I add 3/2 of this to this, I'm going to get 0, because I'm going to have 3/2 y added to -3/2 y. So 3/2 of 0, of course, is 0 added to x. I've still got x. 3/2 of y is 3/2 y added to -3/2 y gives me 0, as I wanted to get. And 3/2 of -1/8 is -3/16. Added to 2 gives me 29/16. So you can check the arithmetic. Well, that means x plus 0 is 29/16, so x is 29/16. I have 32 here. Let's fix that. If I had white chalk, it would be better, but let's go ahead and admit that I made a mistake and put a 16 here. Okay. Now, and this equation is just y equals -1/8. So I know what x and y are to solve this equation. Now, as you should know from Algebra 1, hopefully, at least in Algebra 2, we know that we can graph these two equations, and the point where the graphs cross, of course these are both linear equations, they both have straight line graphs, and the point where the graphs cross is our solution. And that point should be 29/16, -1/8. So let's see if that's possible. Okay, now here I've graphed the two equations. I'm going to come back in a separate video and just talk quickly about how we do the graphs.